What if the universe is not as solid as it looks? What if the stars, galaxies, planets, atoms, and even the quiet space between your thoughts are not resting on an eternal foundation, but balanced on something invisible, delicate, and temporary? Look around in your imagination for a moment. Picture the moon moving silently around Earth. Picture the sun burning with patient nuclear fire. Picture the Milky Way turning like a vast glowing wheel in the dark. Everything feels ancient. Everything feels permanent. But physics whispers a disturbing possibility. Reality may be sitting in a state that only appears stable. And somewhere at some unpredictable moment, a quantum event could begin that would not explode the universe like a bomb, not burn it like a supernova, not crush it like a black hole, but rewrite the rules of existence itself. This event is called vacuum decay, and it is one of the most terrifying ideas in modern physics because it does not need an army, a weapon, a warning, or even a visible cause. It could begin as a tiny quantum fluctuation, smaller than an atom, smaller than a proton, smaller than anything your mind can comfortably imagine. A microscopic bubble could appear in the fabric of space, and if that bubble were the right kind of bubble, it would expand outward at nearly the speed of light. Inside it, the universe would no longer be the universe we know. The masses of particles could change. The forces that bind atoms could change. Chemistry could collapse. Matter could lose its familiar structure. Stars, planets, oceans, cells, memories, and light itself would be swallowed not by darkness, but by a new version of physical law. And the most disturbing part is this. If such a bubble were coming toward us right now, we would never see it. No telescope would warn us. No alarm would sound. No scientist would shout that the end had arrived. Because the signal telling us it was coming would travel at the speed of light, and the bubble itself would also move at the speed of light. The first moment we could know about it would be the same moment it arrived. There would be no fear, no running, no final sunrise. There would simply be the universe we know, and then there would not. Before we go deeper into this strange and terrifying possibility, take a slow breath and stay with me. Because this is not fantasy. This is not a monster from mythology. This is not a fake doomsday story. This is a real scientific idea connected to quantum field theory, the Higgs field, and the question of whether our universe is truly stable. And if you enjoy deep space mysteries, quantum physics, and the hidden dangers buried inside reality itself, then like this video, subscribe, and tell me in the comments, if the universe could end without warning, would you want to know the truth, or would you rather never think about it? Because tonight we're going to walk quietly into one of the deepest questions in science. Is reality safe? To understand this terrifying quantum event, we first have to remove a simple illusion. Most people think empty space is empty. They imagine space as a blank stage where planets and stars move. If you remove all matter, all gas, all dust, all light, you might think nothing remains. But modern physics says the vacuum is not nothing. The vacuum is a physical state. It is the lowest looking arrangement of fields in a region of space, and those fields are not decorations added to the universe. They are the universe at its deepest known level. Every particle you have ever heard of is connected to a field. The electron is not simply a tiny dot flying through emptiness. It is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. The Higgs boson is an excitation of the Higgs field. In this view, the universe is not made of little solid balls floating through nothing. It is more like an invisible ocean of fields, and what we call particles are ripples, vibrations, patterns, and disturbances in those fields. This changes the meaning of empty space completely. Even if you remove every particle from a region, the fields remain. They still have values, they still have energy, they still obey quantum rules. So the vacuum is not a blank absence, it is a condition of the fields. And because fields can have different possible energy states, the vacuum itself can have different possible states. Some vacuum states may be stable, some may only look stable, and that difference is where the terror begins. Imagine a ball resting in a valley. If the valley is deep and there is no lower place nearby, the ball is safe. Small pushes may make it wobble, but it rolls back. This is like a true vacuum, the lowest possible energy state. But now imagine the ball resting in a small valley on the side of a mountain. It seems stable because it is trapped there. It does not roll away on its own. But somewhere beyond the ridge there is a much deeper valley. If the ball somehow crosses the ridge, it will fall into that deeper valley and never return. That first small valley is called a false vacuum. It looks stable locally, but it is not the final lowest state. The terrifying possibility is that our entire universe might be like that ball. We may live in a vacuum state that feels stable, has lasted for billions of years, and has allowed galaxies, planets, atoms, and life to form. But it might not be the true lowest energy state of reality. It might be metastable, stable enough to last for an unimaginably long time, but not absolutely permanent. And quantum physics allows strange things to happen when enough time and enough space are involved. In ordinary life, if a ball is trapped in a valley, it cannot cross the ridge unless it gets enough energy. But quantum objects do not always behave like ordinary balls. Quantum systems can tunnel. They can pass through barriers that classical physics says they should not cross. This is not magic. It is a real, measured, essential part of physics. Quantum tunneling helps explain radioactive decay. It appears in nuclear fusion in stars. It is used in technologies such as tunneling microscopes. Nature allows events that are not impossible, only extremely unlikely. Now imagine that the fields of the universe are trapped in a false vacuum. They do not have enough ordinary energy to climb over the barrier into a lower state. But quantum tunneling might allow a tiny region of space to slip through the barrier anyway. That tiny region would become true vacuum. At first it might be incredibly small, but if it is large enough to be stable, it would expand. Why? Because the true vacuum would have lower energy than the false vacuum around it. The boundary between the two states would rush outward, converting more and more space into the new vacuum state. This is vacuum decay. It is not an explosion inside space. It is a transformation of space. It is not matter destroying matter. It is the vacuum itself changing phase. A useful analogy is water freezing. When a small crystal of ice forms in supercooled water, it can trigger the water around it to freeze too. The new phase spreads. But vacuum decay would be infinitely more fundamental. It would not merely turn water into ice. It would turn the underlying laws of particle physics into something else. Inside a true vacuum bubble, the values of fundamental fields could be different. If the Higgs field changed, particle masses could change. If particle masses changed, atoms might not hold together. Electrons might not orbit nuclei in the way they do now. Protons and neutrons might not remain stable in the same form. The delicate balance that allows chemistry to exist could be destroyed. The rules that let carbon form long chains, that let water behave like water, that let DNA store information, that let stars shine steadily for billions of years, could vanish. This is why vacuum decay is terrifying in a way that ordinary disasters are not. A supernova is violent, but it happens in a place. A black hole is extreme, but it has a horizon and a location. Gamma-ray bursts are deadly across cosmic distances, but they are still events inside the existing laws of physics. Vacuum decay would be deeper. It would not simply kill life. It could remove the possibility of life as we understand it. It could erase the architecture that makes matter meaningful. But before fear takes control, we must be careful. Science is not saying that this will happen tomorrow. Science is not saying that anyone has found proof that our universe is doomed in this way. The important word is possibility. Based on what we know about the Higgs boson and the top quark, some calculations suggest that the vacuum of our universe may be metastable, not absolutely stable. But these calculations depend on precise measurements, and on whether our current theories remain valid at extremely high energies. There may be new physics beyond what we know that makes the universe stable. Supersymmetry, unknown particles, quantum gravity, or deeper field structures could change the story completely. Still, the possibility is real enough that physicists take it seriously as a theoretical question. And the reason it became especially dramatic is connected to one of the most important discoveries in modern science, the Higgs boson. For decades, physicists believed there had to be a field-filling space that gives many elementary particles their mass. Without such a mechanism, the known particles in the standard model would not behave the way experiments showed. This field became known as the Higgs field. Unlike the electromagnetic field, which can be zero in empty space, the Higgs field has a non-zero value even in the vacuum. It is always there. It fills the universe like an invisible presence. When particles interact with the Higgs field, they behave as if they have mass. This does not mean the Higgs field gives all mass in the universe, because much of the mass of protons and neutrons comes from the energy of quarks and gluons inside them. But for fundamental particles like electrons and quarks, the Higgs field is essential. If the Higgs field had a different value, the masses of particles would be different. And if particle masses were different, the universe could be unrecognizable. In 2012, scientists at CERN announced the discovery of a particle consistent with the Higgs boson. It was a monumental confirmation of the Higgs field. But once physicists measured the Higgs boson mass, they noticed something strange. When combined with measurements of the top quark, the numbers seemed to place our universe near the boundary between stability and metastability. Not certainly doomed, not certainly safe, but in an eerie region where the vacuum might be long-lived but not eternal. It was as if the universe had handed us a key and whispered, "You may exist because reality is balanced on an edge." This edge is not like the edge of a cliff in space. It is a mathematical edge in the potential energy of the Higgs field. The Higgs field has a value in today's vacuum, but at extremely high field values, the shape of its energy potential may bend downward. If it bends downward far enough, then there may be a deeper vacuum state elsewhere in field space. Our vacuum would be a local minimum, not the absolute minimum. This is a difficult idea, so let us slow down. A field can have a value, just like temperature has a value in a room. The energy of that field depends on the value it has. The field naturally wants to settle into values with lower energy. Our universe has settled into a value of the Higgs field that gives particles the masses we observe. But the mathematical structure of the Standard Model suggests that at very high energies, the Higgs field might have access to another state with lower energy. If so, our universe is not in the true bottom of the energy landscape. It is in a temporary basin. Temporary does not mean short. A mountain can stand for millions of years. A radioactive atom can have a half-life longer than the age of the universe. A metastable vacuum could last for times so vast that writing them down becomes almost meaningless. The calculated lifetime of our vacuum, if it is metastable, may be enormously longer than the current age of the universe. So this is not a practical danger, in the way asteroids or climate or nuclear weapons are practical dangers. It is a cosmic, philosophical danger. It reveals that existence itself may be probabilistic. And yet the words "extremely unlikely" do not fully comfort the mind, because vacuum decay has a special character. Most threats become less frightening if they are unlikely, but vacuum decay feels different because it has no warning and no defense. You cannot build a shelter from a change in the vacuum. You cannot outrun something moving at light speed. You cannot send a spacecraft beyond it, because there is no outside within the affected region. The event does not move through the universe like a storm across land. It changes what the universe is. Now let us imagine, carefully and scientifically, what would happen if a bubble of true vacuum formed somewhere in the universe. At first, the event would be smaller than microscopic. In a tiny region, the field would tunnel from the false vacuum to the true vacuum. This is called bubble nucleation. But not every tiny bubble survives. If the bubble is too small, the energy cost of its boundary may cause it to collapse. There is a competition between the energy gained by converting space to the lower energy vacuum and the energy required to create the wall between the two vacuum states. Only if the bubble is large enough, larger than a critical size, does it expand instead of disappearing. If it expands, the wall accelerates outward. In many theoretical pictures, it moves at or very near the speed of light. The bubble wall is not made of ordinary matter. It is a transition region where the field changes from one vacuum state to another. Ahead of the wall, everything is normal. Behind the wall, the field has a new value. The universe inside the bubble is governed by different conditions. The first galaxies swallowed by the bubble would not burn or crack or slowly fade. They would be converted. Their particles would no longer be particles in the same vacuum. The structures that made them galaxies would no longer hold. There is no reason to think stars would remain stars, or atoms would remain atoms. A planet entering the bubble would not experience a shockwave first and then destruction. Its existence as organized matter would depend on physical rules that might no longer apply. From outside the bubble, if an observer could somehow survive and see it from far away, the event might be impossible to observe before it reached them because the wall moves at light speed. If it formed beyond our cosmic horizon, it would never reach us because cosmic expansion carries distant regions away. If it formed within our observable universe but far away, it might already be moving toward us, but no information could outrun it. The universe gives no early warning for an event traveling with the fastest possible signal. This creates one of the most haunting thoughts in physics. The end of the universe, if vacuum decay occurs, may not be something that happens in the future for us to anticipate. It may be an event whose approach is permanently hidden. The sky could look perfectly normal one instant before it arrives, but let us not fall into panic. The same physics that allows vacuum decay also suggests that if it were easy, it likely would have happened already. The universe is about 13.8 billion years old and it is huge. Across the cosmos there have been countless high-energy events: supernova, neutron star mergers, black hole collisions, cosmic rays with energies far beyond anything human machines can create. The early universe itself was far hotter and denser than any laboratory experiment. If ordinary high-energy collisions easily triggered vacuum decay, the universe would probably not still be here. This point is important because people sometimes worry that particle accelerators could destroy the universe. The fear usually sounds dramatic. What if smashing particles together at high energy creates a black hole or triggers vacuum decay? But nature has been performing far more energetic particle collisions for billions of years. Cosmic rays slam into planets, moons, stars, and interstellar matter with energies that can exceed our accelerators. If such collisions were capable of triggering vacuum decay under ordinary conditions, it would almost certainly have happened naturally long ago. Particle accelerators are powerful for human technology, but they are not powerful compared with the most extreme natural processes in the cosmos. So the terrifying quantum event is not something scientists are creating in secret. It is a theoretical possibility built into the structure of quantum fields. It is less like a bomb someone might build and more like a hidden property of the universe itself. Now, to feel the full strangeness of vacuum decay, we need to understand quantum tunneling more deeply. In classical physics, a particle behaves like a tiny object following a definite path. If it does not have enough energy to cross a barrier, it cannot cross. But in quantum mechanics, a particle is described by a wave function, which gives probabilities. The wave function can extend into and beyond regions that would be forbidden classically. There is a small chance that the particle will appear on the other side of a barrier without ever having enough energy to climb over it in the ordinary sense. This is not a loophole in reality. It is reality. The sun shines partly because quantum tunneling allows protons to overcome their electromagnetic repulsion and fuse. Alpha particles escape atomic nuclei through tunneling during radioactive decay. Electronics at tiny scales must account for tunneling because electrons can pass through barriers that would be solid walls in classical intuition. Now scale this idea up, not to a single particle, but to an entire field. A field can tunnel from one configuration to another. The ball in a valley analogy helps, but it can mislead because the field is not a little object in ordinary space. It is a value spread across space. Vacuum decay is field tunneling. A region of the field shifts to a lower energy configuration, forming a bubble. The universe may have already experienced events like this in its earliest moments. Some cosmological theories suggest that phase transitions occurred as the universe cooled after the Big Bang. Forces that were once unified may have separated. Fields may have settled into new values. The Higgs field itself acquired its present non-zero value during electroweak symmetry breaking, giving many particles mass. In other words, the universe we know may already be the result of a cosmic phase transition. Vacuum decay would be another transition, but one that would be destructive to our current form of reality. The early universe was not a calm place. It was hot, dense, and filled with intense fields. As it expanded and cooled, its physical state changed. You can think of steam cooling into water, water freezing into ice, or molten metal crystallizing into solid form. Though these analogies are far simpler than the real physics, phase transitions can create structure. They can also release energy. Some theories of cosmic inflation involve fields trapped in false vacuum states, with the universe expanding rapidly until the field transitions to a lower energy state. In that sense, false vacuum is not only a doomsday idea, it may be tied to cosmic creation itself. This is one of the great twists. The same concept that could destroy a universe may also help explain how a universe begins or changes. False vacuum energy can drive expansion. Vacuum transitions can produce bubbles of new physical conditions. In some speculative models, universes may be born through vacuum decay events in a larger cosmic landscape. Our universe might itself be a bubble formed from a previous vacuum state. If that is true, then vacuum decay is not only an ending, it is also a strange kind of cosmic reproduction. But we must separate careful science from speculation. The possibility that our vacuum is metastable is based on known physics extrapolated to energies far beyond what we can directly test. The idea that vacuum bubbles create new universes belongs to broader theoretical cosmology and remains uncertain. We can explore it, but we should not pretend it is proven. The honest scientific position is both thrilling and humbling. We know enough to ask the question, but not enough to close the case. At the center of this uncertainty is the Standard Model of particle physics. The Standard Model is one of the most successful scientific theories ever made. It describes electromagnetic, weak, and strong interactions between known elementary particles. It predicted particles before they were found. It matches experiments with extraordinary precision, yet it is incomplete. It does not include gravity in a quantum way. It does not explain dark matter. It does not fully explain neutrino masses. It does not explain why the universe contains more matter than antimatter. It does not explain dark energy. And it may not remain valid all the way up to the highest possible energies. When physicists use the Standard Model to study vacuum stability, they run the equations upward to extremely high energy scales. The behavior of the Higgs field depends strongly on the top quark, the heaviest known elementary particle. The top quark interacts strongly with the Higgs field, and its mass affects the shape of the Higgs potential at high energies. With current measured values, the universe appears close to a metastable boundary, but small changes in the top quark mass, Higgs mass, or strong coupling can shift the conclusion. Also, unknown physics at high energies could alter the potential completely, so the universe may be stable, it may be metastable, or our current way of asking the question may be incomplete. This uncertainty is not weakness, it is the frontier. It is where science is alive. But let us return to the emotional center of the story. Why does vacuum decay feel so terrifying? It is not merely because it can destroy things. Many cosmic events destroy things. The terror comes from the idea that what we call nothing is not guaranteed. We build our understanding of safety around matter. We worry about objects, asteroids, stars, radiation, black holes. But vacuum decay says the deepest danger may not be an object at all. It may be the state of the empty space that allows objects to exist. Every room you have ever entered, every sky you have ever seen, every quiet night, every breath, every heartbeat has been supported by the same vacuum state. You do not feel it because it is everywhere. The Higgs field does not announce itself. Quantum fields do not glow in the dark, yet they define the behavior of every particle in your body. Your atoms are possible because electrons have the mass they have. Chemical bonds exist because electromagnetic forces and quantum rules balance in precise ways. Nuclei exist because quarks, gluons, protons, neutrons, and forces behave within certain ranges. Change the vacuum deeply enough, and the body is not merely harmed. The concept of a body loses meaning. That is what makes this idea so cosmic and so intimate at the same time. Vacuum decay is about the fate of galaxies, but it is also about why your hand can exist, why your thoughts can form, why the word existence means anything at all. Now imagine the universe as a sleeping ocean. On the surface, galaxies drift like glowing foam. Stars rise and die. Planets cool. Life appears in rare places, perhaps many places, perhaps only a few. Civilizations ask questions. Telescopes open. Equations are written. And beneath all of this, the ocean floor may not be the lowest floor. There may be a deeper drop hidden under the calm. The universe is not fragile in the ordinary sense. It has survived violent events beyond imagination. Stars have exploded. Black holes have merged. Entire galaxy clusters have collided. The vacuum did not decay. That tells us something important. If our vacuum is metastable, it is extraordinarily long-lived. It is not like thin ice cracking under every step. It is more like a diamond balanced in a mathematical possibility, so rare that cosmic history itself becomes evidence of its durability. But quantum probability is patient. In a metastable system, the chance of decay per unit volume per unit time may be incredibly tiny. Yet the universe contains vast volume and vast time. If the probability is not zero, then given enough future, decay may eventually occur. This is where the mind meets infinity and becomes uncomfortable. A thing can be practically impossible now and still inevitable across unimaginable timescales. However, even inevitable can be misleading in cosmology. The universe is expanding. Distant regions move away from us due to the expansion of space. The observable universe is limited by horizons. If a vacuum decay bubble forms far enough away, cosmic expansion may prevent it from ever reaching us. In some models, space expands so quickly in distant regions that bubbles cannot convert everything. This leads to strange pictures of eternal inflation, where different regions transition into different vacua, forming a patchwork or multiverse. Again, this is speculative, but it shows that the universe may not be a simple single object with one ending. For us, the practical question is smaller and more haunting. Could a bubble form within our reachable cosmic region? The answer is theoretically yes, if the vacuum is metastable. But the expected timescale, according to many studies using known physics, is vastly longer than the current age of the universe. The universe is about 13.8 billion years old. Vacuum decay, if it occurs under these assumptions, may be so unlikely that the expected lifetime is not billions, not trillions, but numbers with an absurd number of zeros. That does not make the idea false, it makes it remote. So this video is not a warning to live in fear, it is an invitation to awe. The terror of vacuum decay is not the terror of immediate danger, it is the terror of discovering that even the most basic layer of reality may have a hidden history and a hidden future. Let us now explore what the new vacuum might actually be like. Many people imagine that a vacuum decay bubble simply destroys everything and leaves nothing. But scientifically, the result depends on the lower energy vacuum state. It might be a universe with different particle masses, different force behavior, perhaps no stable atoms. It might collapse gravitationally. It might expand with different vacuum energy. It might be empty in the sense that complex structures cannot exist. Or it might have its own strange physics, not friendly to us, but not necessarily nothing. If the Higgs field value changed dramatically, electron mass might change. The masses of quarks might change. This would alter protons, neutrons, atoms, nuclear stability, and chemistry. Even small changes in fundamental constants can have enormous consequences. If electrons were much heavier or lighter, atomic sizes and chemical bond energies would shift. If quark masses changed, some nuclei might become unstable. If the balance between proton and neutron mass changed, hydrogen might not exist in the same way, and stars might not burn as they do. Our universe is a delicate system. The word delicate does not mean designed, it means constrained. Complex structure emerges only in certain ranges of physical parameters. The strong force must bind nuclei, but not too differently. Electromagnetism must allow atoms and molecules. Gravity must be weak enough for stars to last, but strong enough to gather matter. The cosmological constant must not tear structures apart too quickly. The Higgs field must give particles masses that permit chemistry. We live in a universe where the numbers allow observers. Vacuum decay could change those numbers instantly. This is why some physicists speak of the landscape of possible vacua. In certain theories, especially involving string theory, there may be many possible vacuum states, each with different low-energy physics. Our universe would be one valley among many. Vacuum decay would be a transition from one valley to another. The laws of physics we observe would not be the only possible laws, but local laws determined by the vacuum state. This is a profound shift in perspective. It suggests that what we call the laws of nature may be partly environmental, like the climate of a region in a much larger reality. Again, this landscape idea is not experimentally confirmed, but it is powerful because it gives a framework for thinking about vacuum states. It turns reality into something like a cosmic geography of possibilities. Some valleys may allow stars, some may allow nothing complex, some may expand rapidly, some may collapse, some may be unreachable. And we are sitting in one valley measuring its shape, wondering whether it is the deepest one. Now, what about black holes? Could black holes trigger vacuum decay? This is a serious theoretical question. Black holes create extreme space-time curvature, and are connected to quantum gravity, which we do not fully understand. Some studies suggest that under certain conditions, tiny primordial black holes might catalyze vacuum decay. Other analyses depend strongly on assumptions about high-energy physics. We should not state this as a known threat. Ordinary astrophysical black holes have existed for billions of years, and the universe remains. But black holes remind us that the places where our theories overlap, quantum fields, gravity, extreme energy, are exactly the places where unknown physics may matter. The early universe may also have threatened itself. During the Big Bang's earliest fractions of a second, energies may have been high enough for fields to explore dangerous regions. Inflation, reheating, quantum fluctuations, and thermal effects could have influenced vacuum stability. Yet the universe survived into the cool, structured state we see. That survival is evidence that either the vacuum is stable or metastable with an incredibly low decay rate, or protected by physics we have not yet discovered. There is another twist. The measured Higgs boson mass may be oddly close to the boundary of metastability. Some physicists find this intriguing. Why should the universe sit near such a boundary? It might be coincidence. It might reflect deeper principles. It might be shaped by selection effects. Perhaps observers can only arise in regions where the vacuum lasts long enough and physical constants fall into life-permitting ranges. Or it might be a clue that our theories are missing something. Science does not yet know. This boundary-like quality gives the story its eerie beauty. The universe may not be confidently stable or quickly doomed. It may be balanced in a vast middle state, stable enough for galaxies and life, but not guaranteed forever. It is like a candle flame that has burned for billions of years in a windless room, and only after studying the flame deeply do we realize the room itself is part of a larger storm. Now let us talk about time. Human fear is shaped by human time. A danger next year frightens us. A danger in 1,000,000 years feels abstract. A danger in 10 to the power of 100 years becomes almost meaningless. Vacuum decay, if real, probably belongs to that deep time category. It is not a threat to your daily life. It is not a reason to panic. The scientifically honest emotional response is not panic, but awe mixed with humility. The universe has many possible endings. Stars will eventually exhaust their fuel. Galaxies will change. The sun will one day leave the main sequence and make Earth uninhabitable long before vacuum decay is likely to matter. On very long timescales, star formation may cease. Black holes may dominate. If proton decay exists, matter itself may slowly dissolve. Black holes may evaporate through Hawking radiation over immense times. The far future may become cold, dark, and dilute. Vacuum decay is different because it could interrupt any of these slow endings. It is a sudden ending hidden inside a universe otherwise moving slowly toward entropy. In a heat-death scenario, the universe fades. In a big crunch, it collapses. In a big rip, expansion tears structures apart. In vacuum decay, the universe changes identity. That phrase matters. Changes identity. It is not simply that things die. It is that the rules by which things are defined no longer apply. Let us imagine a civilization far in the future, advanced beyond anything we know. Suppose they can move stars, build habitats around black holes, harvest energy from galaxies, survive supernova, cross interstellar distances, and manipulate matter with near-perfect skill. Could they survive vacuum decay? Almost certainly not if it reaches them. Technology depends on physical law. You can defeat an asteroid because you exist in the same physics as the asteroid. You can shield radiation because atoms and fields behave predictably. But a vacuum decay bubble changes the ground under every tool. There is no engineering solution to the sudden replacement of the vacuum state. Could such a civilization detect that the vacuum is unstable? Maybe they could measure particle properties more precisely, discover deeper theories, and calculate the risk. But knowing would not necessarily give control. Could they trigger a safe transition? Could they create a bubble and contain it? The answer, with known physics, is no. A true vacuum bubble, once expanding, would not be a controllable fire. It would be a cosmic phase boundary, but such questions move into speculative territory. The known lesson is simple. Some cosmic risks are not problems to solve, but truths to understand. And perhaps that is why vacuum decay is so powerful for the imagination. It reveals a limit to control. Modern humans often think of knowledge as a path to mastery. We learn the atom and we build electronics. We learn genetics and we edit life. We learn gravity and we send spacecraft. But vacuum decay is knowledge that may not empower us directly. It humbles us. It says, reality may have conditions deeper than survival. Now let us bring this back to the present moment. You are listening to words formed by air pressure waves or digital signals. Those signals depend on electrons moving through circuits. The circuits depend on semiconductors. Semiconductors depend on quantum mechanics and band structures. Band structures depend on electron mass, electromagnetic interactions, atomic lattices, and the stability of matter. Your brain interprets the sound through neurons, molecules, ions, proteins, water, membranes, and chemical gradients. All of this depends on the vacuum state. The empty space inside and around every atom is not truly empty. It is governed by fields. The stability of the vacuum is silently involved in every ordinary experience. This is the hidden poetry of physics. The most terrifying ideas are often hidden inside the most peaceful moments. A quiet room is only quiet because the vacuum permits atoms to remain atoms. A starry sky is only beautiful because fields have settled into values that allow light to travel, nuclei to fuse, and planets to form. Reality is not a dead stage. It is an active agreement among fields. If the vacuum is metastable, then every moment is the continuation of that agreement. Now, there is a question people naturally ask. If a bubble of true vacuum expands at the speed of light, would it destroy the entire universe in seconds? The title says it could destroy the universe in seconds, but we must be precise. Locally, once the bubble reaches any region, that region is transformed essentially instantly. If it formed near Earth, Earth would be gone in less than a fraction of a second. The solar system would be swept quickly. The Milky Way, about 100,000 light-years across, would take about 100,000 years for a light-speed bubble to cross from one side to the other if it began at one edge. The observable universe is billions of light-years across, so converting it all would take billions of years from an outside cosmic perspective. But for any observer in its path, there is no warning. If the bubble formed close enough, our world could end in seconds. If it formed at Earth, the change would be immediate. If it formed within the solar system, light-speed expansion would cross planetary distances in minutes or hours. If it formed just beyond the Moon, it would arrive in about a second. If it formed near the Sun, it would arrive in about 8 minutes. The terror is not that the whole observable universe becomes transformed in a few seconds from one global viewpoint. The terror is that any local region can be erased without warning, and if the event begins nearby, everything familiar can vanish in seconds. This distinction keeps the science honest. Vacuum decay is not a cinematic explosion instantly covering billions of light-years faster than light. It respects relativity. The bubble wall cannot send information faster than light. Its speed is terrifying precisely because light speed is the cosmic speed limit. It is the fastest possible arrival and therefore the least warning possible. Could we see distant galaxies disappearing as a vacuum bubble crossed them? Only if the bubble were not coming directly toward us, and if light from affected regions reached us before the bubble did. But because the bubble wall moves at light speed, any light emitted at the moment of destruction would travel alongside the wall. If the bubble is headed toward us, we would not see the destruction before arrival. If it moves in another direction, maybe there are complicated observational possibilities, but in practice, detecting such an event would be profoundly difficult. Vacuum decay is not like a fire spreading across the night sky. Now let us consider the energy released. A false vacuum has higher energy than a true vacuum. When a region transitions, the energy difference must go somewhere. It may contribute to the kinetic energy of the bubble wall, radiation, particles, gravitational effects, or the expansion behavior of the new vacuum. The details depend on the theory. In some cases, a vacuum transition could release enormous energy. In others, the interior might behave like a universe with negative vacuum energy and collapse. These possibilities are theoretical and depend on the shape of the potential. This uncertainty is important because it means no one can honestly describe exactly what the inside of the bubble would look like. We can say that our kind of matter likely would not survive if fundamental field values change drastically, but the precise after is unknown. There might not be an after in any meaningful sense for observers like us. The word destroy can also be subtle. If vacuum decay converts our universe into a new vacuum state, is that destruction or transformation? From our perspective, it is destruction. From a wider theoretical perspective, it is a phase transition. Nature does not label it tragedy, physics does not mourn. The same universe that gives birth to stars also allows black holes. The same quantum rules that allow chemistry also allow tunneling. The cosmos is not cruel, it is indifferent in ways that become terrifying only because we are conscious. But consciousness is also what makes the story beautiful. The universe has produced beings capable of asking whether the universe itself is stable. Atoms organized into brains have begun to examine the vacuum that permits atoms to exist. This is one of the deepest loops in science. Reality becomes aware of its own possible impermanence. Now let us go deeper into the Higgs field again, because it is the heart of this mystery. The Higgs field has a present value often described as its vacuum expectation value. This value is not zero, it fills space. Particles interacting with it acquire mass. The Higgs boson is a ripple in this field, like a wave on an invisible sea. When CERN detected the Higgs boson, it confirmed that the field is real in the sense required by the standard model. But the Higgs field's potential energy shape is influenced by quantum corrections. In quantum field theory, particles are not isolated simple objects. Fields affect one another. Virtual processes, loops, and interactions modify the effective potential. The top quark, because it is heavy and strongly coupled to the Higgs field, pulls the potential in a way that can destabilize it at high field values. The Higgs boson mass pushes in another way. The measured values seem to make the potential flatten and possibly dip at extreme scales. This is why the top quark matters so much. The top quark is not part of ordinary atoms. It decays too quickly to form normal matter, yet its mass may influence the ultimate stability of the entire vacuum. A particle that almost never appears in everyday life may help decide whether reality is absolutely stable. That is a twist worthy of the cosmos. The fate of everything may depend partly on the properties of one of the most short-lived particles known. The top quark lives for an unimaginably brief time before decaying. It is produced in high-energy collisions and studied in particle accelerators. It is heavy, far heavier than protons or neutrons. Its relationship with the Higgs field is strong. If its mass was slightly different, the stability calculation could shift. This makes precision measurement not just technical work, but cosmic detective work. Every decimal place matters because every decimal place may alter our picture of reality's foundation. The Higgs boson mass also matters. If the Higgs had been much lighter or heavier, the vacuum stability story would look different. The measured Higgs mass sits in a region that makes the question dramatic. Some scientists have called this near criticality. It may be coincidence, but physics has often advanced by paying attention to coincidences. When numbers appear strangely balanced, they may be telling us something, or they may simply be the outcome of a vast cosmic lottery. Now, another natural question. Could dark energy be related to this? Dark energy is the name we give to the mysterious cause of the accelerated expansion of the universe. It behaves like a small positive energy of empty space, or perhaps something more dynamic. Vacuum energy is central to quantum field theory, but the observed value of dark energy is incredibly tiny compared with naive quantum predictions. This is the cosmological constant problem, one of the deepest unsolved problems in physics. Vacuum decay and dark energy both involve the vacuum, but they are not the same thing. Vacuum decay concerns a transition between field states. Dark energy concerns the energy density driving cosmic acceleration. However, in a broader sense, both remind us that empty space has properties. The vacuum is not nothing. It can shape the fate of the universe. If our vacuum decayed into a lower energy state, the vacuum energy inside the bubble could be different. If it were negative, the interior might collapse. If positive, it might expand differently. These are complex possibilities, but they show that vacuum decay is not merely particle physics. It touches cosmology, the large-scale future of space and time. Now let us talk about probability. People often misunderstand rare quantum events. They may think, if it can happen, why has it not happened already? But rare events can have half-lives vastly longer than current time. Some isotopes decay quickly, others persist. Some quantum tunnelings occur constantly, others are so suppressed that they are effectively absent for any human timescale. Vacuum decay depends on the shape and height of the barrier between false and true vacuum. If the barrier is thick or high, in the relevant mathematical sense, tunneling is fantastically suppressed. The decay rate is often calculated using methods involving instantons or bounce solutions in quantum field theory. These are advanced mathematical tools that estimate the probability for a field to tunnel through a barrier. The result can be exponentially sensitive to parameters. That means small changes in the theory can produce enormous changes in the lifetime. This is another reason humility is necessary. We are extrapolating known physics into extreme realms, and exponential calculations magnify uncertainty. But the survival of the universe is itself a constraint. If a theory predicted rapid vacuum decay, it would conflict with the obvious fact that we are here. This is not a joke, it is a scientific filter. Any realistic model must allow the vacuum to survive at least long enough for stars, planets, and observers to form. The current universe has endured intense conditions, so the decay rate must be low or protected. Some people ask whether quantum observation could trigger vacuum decay. The answer is no in the popular sense. Looking at the universe does not collapse the vacuum into destruction. Consciousness does not destabilize fields. Quantum measurement is often misunderstood, but vacuum decay is not caused by someone observing reality. It is a spontaneous quantum process governed by field dynamics. Your thoughts are not dangerous to the cosmos. Others ask whether aliens could intentionally trigger vacuum decay as a weapon. With known physics, this is not realistic. To trigger vacuum decay deliberately, one would need to create conditions that nucleate a critical bubble of lower vacuum. If this were possible at achievable energies, natural cosmic events likely would have done it. It is not impossible to imagine unknown physics or advanced civilizations in science fiction, but scientifically, we have no evidence that vacuum decay can be weaponized. Could a laboratory ever test vacuum decay? Not directly for our universe, because triggering it would be catastrophic if possible. But physicists can study analog systems. Certain materials, fluids, cold atoms, or field-like systems can mimic false vacuum decay behavior in controlled settings. These analogues do not endanger the universe. They help study the mathematics of phase transitions and tunneling. In the same way, a water tank can mimic some wave behavior without becoming an ocean. Analog experiments can teach us about field transitions without changing fundamental reality. This is a beautiful pattern in science. We cannot hold the universe in our hands, but we can create small systems that echo its principles. We study ripples to understand waves, atoms to understand stars, particle collisions to understand the early universe, and condensed matter systems to understand symmetry breaking. The universe repeats patterns across scales, not exactly but suggestively. Symmetry breaking is another key concept. In physics, a symmetry exists when a system remains unchanged under certain transformations. The early universe may have had higher symmetries that later broke as it cooled. When a field chooses a particular vacuum state, symmetry can break. The Higgs field breaks electro-weak symmetry, separating electromagnetic and weak forces in the form we observe. Without this, particles would behave very differently. A vacuum transition can therefore change symmetries. It can decide which forces appear distinct, which particles have mass, which interactions dominate. This is why vacuum states are not passive. They define the rules. The vacuum is like the silent grammar of the universe. Change the grammar, and every sentence of matter becomes unreadable. Now, let us take a meditative cosmic journey. Imagine traveling outward from Earth. You rise above the clouds, above the blue atmosphere, above satellites, above the moon. Earth becomes a luminous marble. The sun becomes a blazing sphere. The planets become scattered points. You travel beyond Neptune, beyond the Kuiper belt, into the deep dark where the sun is just a bright star. Still, the vacuum around you is the same vacuum. The fields have the same values. Atoms still work. Light still moves at the same speed. You cross interstellar space. You pass red dwarfs, white dwarfs, nebulae, molecular clouds. You approach the galactic center where stars crowd around a supermassive black hole. The vacuum remains. You leave the Milky Way. You see Andromeda ahead. Dwarf galaxies drifting, clusters shining, filaments stretching across cosmic space. Everywhere, the same invisible field state supports existence. Now imagine somewhere in that vastness, in a region no telescope is watching, a tiny bubble appears. No sound, no flash visible ahead of it, no warning. It begins expanding, It crosses dust, gas, stars, worlds. It does not care whether those worlds are dead or living. It does not know beauty. It does not know history. It simply converts one vacuum to another. For millions of years, perhaps billions, it travels. If it is far enough, expansion may keep it away. If not, one day its future light cone intersects ours, but there is still no message before arrival. The sky remains calm. Astronomers continue measuring galaxies. Children continue learning the names of planets. Waves continue touching shorelines. The bubble approaches at the limit of causality. And then, without transition experienced by us, the story ends. This thought can feel cold. But there is another way to see it. If there would be no warning and no suffering, then vacuum decay is not a fear we can use. It is not like a disaster we must prepare for. It is a reminder of the strangeness of existence. It turns the ordinary present into something precious. The fact that the vacuum has not decayed is not a guarantee of eternity, but it is a condition of every moment we receive. Science often deepens gratitude by removing certainty. The sun is not a perfect eternal lamp. It is a star with a lifetime. Earth is not the center of creation. It is one planet. The Milky Way is not the whole universe. It is one galaxy. Matter is not solid in the naive sense. It is quantum fields and forces. And now, perhaps, the vacuum is not absolutely final. It may be a metastable state. Each discovery makes us smaller, but also more awake. Let us examine the phrase, destroy the universe. In physics, the universe can mean all of space-time, or it can mean our observable universe, or it can mean our vacuum region. Vacuum decay might not destroy space-time itself. It might create a new region with different vacuum properties. If space continues inside the bubble, then something remains. But from the perspective of all structures built in our vacuum, destruction is accurate. It would erase the universe as we know it. This distinction matters because reality may be larger than our cosmic patch. In eternal inflation models, many bubble universes can form in a larger inflating background. Each bubble may have different physics. If our vacuum decays, it may be one transition in a vast landscape. The total multiverse, if it exists, might continue, but our universe, our stars, our constants, our chemistry, would end. Do not confuse this with parallel universes in pop culture. The scientific multiverse is not necessarily a place where alternate versions of you walk around. It may be a collection of regions with different vacuum states, separated by cosmic expansion or by the structure of space-time. It is speculative, mathematical, and difficult to test. But vacuum decay naturally fits into such discussions because different vacua can produce different physical laws. Now, what is the true vacuum? The phrase sounds comforting, as if true is better than false. But in physics, true vacuum simply means lower energy, not better for life. A true vacuum could be completely hostile to complexity. The false vacuum may be the only reason we exist. This is another cosmic irony. The false state may be the life-giving state. The true state may be empty, collapsed, or sterile. Truth in energy does not equal meaning in life. The universe does not owe survival to the deepest valley. This idea echoes across science. Stars are temporary structures fighting gravity with fusion. Life is a temporary order, fighting entropy with energy flow. Atoms are stable patterns in quantum fields, not tiny eternal stones. Galaxies are temporary arrangements shaped by gravity, dark matter, and cosmic expansion. Everything we call real may be a stable enough pattern, not an eternal object. Vacuum decay extends this pattern to the foundation itself. Now let us address a subtle misconception. If the universe is in a false vacuum, why does it not constantly leak energy or show signs of instability? Because a metastable state can be extremely stable against ordinary disturbances. A diamond is metastable relative to graphite under everyday conditions, but your diamond ring does not instantly turn into pencil lead. It remains because the transition is blocked by energy barriers. Similarly, a false vacuum can persist because the transition to true vacuum is suppressed. It is not weak in daily conditions. This analogy is not perfect, but it helps. Metastability is common. Supercooled water can remain liquid below freezing until disturbed. A pencil balanced on its tip is unstable, but a ball in a shallow valley beside a deeper valley is metastable. The universe, if metastable, is not necessarily trembling on a knife edge. It may be settled in a basin separated from disaster by a barrier so enormous in quantum terms that decay is fantastically rare. So why talk about it at all? Because it reveals the deep structure of physical law. It connects the smallest quantum fluctuations to the largest cosmic fate. It shows how measurements in particle physics can influence our understanding of the future of the universe. It proves that the word vacuum hides one of the most profound mysteries in science. Now let us think about what would happen to light inside a changed vacuum. The speed of light in vacuum is tied to the structure of space-time and electromagnetic fields. If the vacuum state changed radically, photons as we know them might not remain massless, or electromagnetism might behave differently, depending on the symmetry structure of the new vacuum. If photons acquired mass, light would not travel infinitely in the same way. If charged particles change masses or interactions, atoms would not emit the same spectra. The colors of the universe would lose meaning. Imagine a star entering the bubble. A star is a balance between gravity pulling inward and pressure from fusion pushing outward. Fusion depends on quantum tunneling, nuclear forces, particle masses, and temperatures. If particle masses and forces changed, fusion could stop or become impossible. But even before talking about fusion, the matter composing the star might no longer be stable. The star would not have time to adjust. Its identity as plasma governed by our physics would be erased. Imagine a planet entering. Rock is crystal structure and chemical bonds. Water is molecular geometry and hydrogen bonding. Atmosphere is gases following thermodynamics. Life is chemistry in motion. Change the vacuum, and all these layers fail at once. There is no dramatic earthquake because there is no stable ground for an earthquake to shake. Imagine a human brain entering. Neurons rely on ion channels, electrical potentials, proteins, and molecular interactions. Consciousness, whatever its full explanation, depends on physical processes in this stable vacuum. Vacuum decay would not be experienced as pain or darkness. It would remove the physical basis of experience. The final moment would not be a moment inside the bubble. It would be the boundary where our story cannot continue. This is perhaps merciful if one can use that word. Vacuum decay would not be an apocalypse of suffering. It would be an apocalypse of absence. No one would watch it happen to themselves. No one would write the final message. The universe would not slowly scream. It would simply be otherwise. But the fact that we can imagine it creates a strange emotional echo. We're safe from it in any practical sense, yet the possibility makes existence feel transparent. It is like learning that the floor under a palace is not stone, but a mathematical agreement that has held so long everyone forgot it was an agreement. Now let us talk about experimental evidence. Have we observed any sign of vacuum decay? No. Have we observed a true vacuum bubble? No. Have we measured the Higgs field? We have strong evidence for the Higgs field through the Higgs boson and particle physics experiments. Have we proven our vacuum is metastable? No. Current theoretical analysis suggests metastability may be possible, but the conclusion depends on measurements and assumptions. This distinction is crucial. A responsible script must not say, the universe will definitely decay. It must say, modern physics allows the possibility, and some calculations suggest our vacuum may be metastable, but this is uncertain and likely involves timescales far beyond human relevance. That may sound less sensational, but it is more powerful because it is true. Reality does not need exaggeration. The honest version is already astonishing. Now, if the universe is stable, then vacuum decay will never occur from our state. The Higgs potential may not have a deeper minimum, or new physics may stabilize it, or quantum gravity may change the calculation. If so, the terrifying event is a door that mathematics allowed us to imagine but nature locked shut. That would be comforting. But even then, the investigation teaches us something. Stability is a question, not an assumption. This is the spirit of science. It does not accept the universe at face value. It asks whether the ground has deeper layers. It tests what empty means. It measures particles that live for tiny fractions of a second and uses them to infer the fate of cosmic time. It takes the invisible seriously. Let us explore quantum fields more poetically but accurately. A field is something that has a value at every point in space and time. The temperature in a room is a field in a loose everyday sense. The wind velocity across a landscape is a field. In fundamental physics, fields are more basic. They are not made of particles. Particles are excitations of fields. The electron field exists everywhere, and an electron is a quantum excitation of that field. The electromagnetic field exists everywhere, and a photon is an excitation of it. The vacuum is the state of these fields when no particles are present. But quantum fields cannot be perfectly still in the classical sense. Quantum fluctuations arise from the uncertainty principle. The vacuum has structure. It can affect measurable phenomena such as the Casimir effect, Lamb shift, and spontaneous emission. These do not mean the vacuum is packed with little real particles popping in and out like tiny sparks in a cartoon. That image is oversimplified. But they do mean vacuum has quantum properties. False vacuum decay is not caused by ordinary virtual particles popping into existence. It is a transition of field state. The field configuration tunnels. The bubble is a region where the field has shifted to a lower energy arrangement. The wall is where it changes between states. This is a collective field-level event. Now consider the phrase "in seconds" again. If a critical bubble formed inside this room, the room would be transformed before any human nervous system could process it. If it formed near Earth, Earth would vanish essentially immediately. If it formed at the Moon's distance, it would arrive in about 1.3 seconds. If it formed at the distance of the Sun, about 8 minutes. If it formed at the nearest star system, years. The speed of light sets the schedule. Locally, seconds are enough. Cosmically, the spread is light years per year. This creates another twist. The universe could be dying somewhere and still look alive here for billions of years, depending on distance and expansion. In relativity, there is no universal cosmic now that everyone shares in the simple human sense. Events are connected by light cones. Vacuum decay would spread through causal structure. It would not violate relativity. It would be one of the most extreme expressions of relativity. No information can warn you faster than the event itself. Now let us ask whether a bubble could stop. In simple models, once a true vacuum bubble surpasses critical size, it expands without stopping because converting false vacuum to lower energy true vacuum is energetically favored. But in an expanding universe with gravity, bubble dynamics can be more complex. Space-time curvature, vacuum energy differences, and cosmic expansion matter. Some bubbles may not reach certain regions due to expansion. Some may create separate space-time regions. These are advanced topics, and the details depend on the model. But for a bubble that reaches us, there is no known way to stop the wall. Could another bubble collide with it? In some cosmological models, bubble collisions can occur. They might leave signatures in cosmic microwave background patterns, though no confirmed evidence exists. Bubble collisions in eternal inflation are speculative but studied. If different vacuum regions expand, their walls may meet. What happens depends on their properties. Again, this is far beyond direct experiment, but it shows how vacuum decay can be part of a larger cosmic ecology. The cosmic microwave background is the oldest light we can observe directly, released when the universe became transparent about 380,000 years after the Big Bang. It gives us a baby picture of the universe. If there had been certain violent vacuum transitions or bubble collisions in our observable past, they might have left patterns. Scientists search for anomalies, but nothing has proven such events. The universe we observe is remarkably uniform on large scales, with tiny fluctuations that seeded galaxies. This uniformity constrains dramatic early events. Now one might ask, if the universe was hotter in the past, could heat push the vacuum over the barrier instead of tunneling? Yes, thermal effects can influence vacuum transitions. At high temperatures, fields can transition over barriers more easily. The early universe's thermal history matters for stability. If dangerous transitions were thermally likely, they would have happened early. The fact that we are here implies the thermal path did not destroy our vacuum, or conditions were different, or new physics protected it. At today's cold cosmic temperature, quantum tunneling is the main concern for spontaneous vacuum decay. The universe is much cooler and more dilute than it once was. The cosmic microwave background is only a few Kelvin above absolute zero. Space is not completely empty, but compared with the early universe, it is quiet. If vacuum decay occurs now, it would be through an extremely rare quantum event, not ordinary heat. Now let us reflect on scale. Humans are intermediate creatures. We are much larger than atoms and much smaller than galaxies. Our intuition was shaped by rocks, rivers, animals, weather, and fire. Quantum field theory operates far below intuition. Cosmology operates far above it. Vacuum decay connects both ends. A quantum fluctuation smaller than a particle could determine the fate of cosmic structures larger than imagination. This is why physics feels almost mythic, even when it is mathematical. Ancient myths often imagine the world ending through fire, flood, darkness, or divine judgment. Modern physics gives us endings stranger than myth. Space-time expansion tearing apart galaxies, black holes evaporating over impossible times, protons perhaps decaying, and vacuum itself transitioning to a new state. These are not stories invented to frighten children. They are consequences of equations tested in laboratories and extended with caution into the unknown. But unlike myth, science includes uncertainty. It does not say, "This will happen," unless evidence demands it. It says this may be possible under these assumptions. That humility makes it stronger. Now, why does the universe have a vacuum state at all? In quantum field theory, the vacuum is the ground state or lowest energy state available under given conditions. But with multiple fields and interactions, the energy landscape can be complicated. Fields can settle into local minima. Symmetry, temperature, expansion, and quantum corrections all matter. The universe, after the Big Bang, may have rolled or tunneled through different field configurations before settling into ours. The Higgs field's current value is not arbitrary in the Standard Model. It arises from the shape of its potential. At high temperatures, the Higgs field may have had zero value, meaning electroweak symmetry was unbroken. As the universe cooled, the field shifted to a non-zero value. This gave particles mass in the way we observe. The details of this electroweak phase transition are important for theories of matter-antimatter asymmetry, though the Standard Model alone may not provide enough CP violation or the right kind of transition. This is another place where new physics may exist, so the Higgs field is not merely a particle discovery. It is connected to why the universe changed from its early symmetric state into the structured reality we know. It may also be connected to whether that reality is final. Now let us imagine the energy landscape in a darker way. You are walking at night through a valley. The ground under your feet feels flat. You can build houses there. Generations can live there, maps can be drawn. But beyond the fog, the valley slopes toward a deeper abyss. A wall of stone separates your valley from it. No ordinary traveller can cross. But quantum mechanics is not an ordinary traveller. Over immense time, there is a tiny chance that a door appears through the wall. If one small patch of land falls into the deeper abyss, the cliff edge begins racing outward. The entire valley is consumed. This is only an analogy, but it captures the emotional shape. Our vacuum is the valley. Quantum tunneling is the impossible door. The true vacuum bubble is the racing cliff edge. Now consider the role of gravity. In flat space-time, vacuum decay calculations are already complex. With gravity, they become even deeper. Gravity responds to energy, and vacuum energy affects space-time curvature. A lower energy vacuum may have different curvature. If the true vacuum has negative energy density, the interior might resemble anti-de Sitter space and collapse. If positive, it might resemble de Sitter expansion. The bubble wall itself has energy and tension. General relativity and quantum field theory must work together, but we do not yet have a complete theory of quantum gravity. This means vacuum decay sits near the border of known physics. We can study it with semi-classical methods, but the full story may require a theory beyond the Standard Model and general relativity. This is another reason not to overclaim. The universe's true stability may be decided by physics we have not discovered. Quantum gravity may forbid certain decays, alter rates, or change the meaning of vacuum states. Planck-scale physics, where gravity becomes quantum, could reshape the Higgs potential at high fields. Unknown particles could stabilize the potential before it turns dangerous. Dark matter interactions with the Higgs field could matter. Neutrino physics could matter. We do not know. The apparent metastability might be a clue pointing toward new physics. This is exciting. A terrifying possibility becomes a research map. Instead of merely fearing vacuum decay, physicists ask what it teaches about particle masses, high-energy scales, cosmology, and unknown laws. The question, will the universe decay, becomes, what is the complete structure of reality? Now, let us talk about cosmic rays again. because they provide a powerful reassurance. Ultra-high energy cosmic rays strike Earth's atmosphere with energies far beyond those in our accelerators, in the center of mass or lab frame depending on comparison, and cosmic collisions have occurred throughout the universe for billions of years. Dense astrophysical objects also experience extreme particle interactions. If dangerous bubble nucleation could be triggered by particle collisions at accessible energies, nature would have triggered it many times. The continued existence of white dwarfs, neutron stars, planets, and cosmic structures is evidence against simple accelerated doomsday scenarios. This does not prove vacuum decay impossible. It shows that human experiments are not the relevant threat. The relevant process, if any, is a spontaneous quantum tunneling event at field scales not achieved by ordinary collisions, or perhaps processes involving extreme unknown conditions. So the fear should not be directed at science experiments. In fact, science experiments are how we learn whether the fear is misplaced. The Large Hadron Collider did not endanger the universe by discovering the Higgs. It gave us information. It allowed physicists to ask the vacuum stability question more precisely. Knowledge did not create the risk. It revealed a possibility already present in the equations. This is an important moral lesson. Ignorance does not make the universe safer. It only makes us less aware of its depth. Now let us slowly build the final scenario from beginning to end. Somewhere in space-time, perhaps unimaginably far away, perhaps never in our future, the Higgs field or a related field experiences a quantum tunneling event. A small region slips into a lower energy vacuum. At first, the bubble is so small that no ordinary concept can picture it. But it is larger than the critical threshold. The wall forms, the energy difference drives expansion, the wall races outward. Inside, the Higgs field has a different value. Particle masses change. The standard model as we know it no longer describes ordinary matter in the same way. Atomic structures fail. Nuclei may destabilize. Electromagnetism may change. The meaning of light may shift. The interior may collapse, expand, or become a sterile new phase. Outside, nothing knows yet. Galaxies continue shining because causality protects ignorance until the wall arrives. The bubble crosses intergalactic space. There is no sound because space carries no ordinary sound across vacuum. There is no visible front that can be seen in advance. It is not a wave of fire. It is a boundary of law. A civilization in its path continues living normally until the final instant. Their instruments show normal physics because physics is normal until it is not. Their clocks tick. Their atoms hold. Their thoughts continue. Then the wall arrives at light speed, and their world is no longer in the old vacuum. If the bubble began near enough to us, the transformation of Earth could happen in seconds. If it began far away, it might take millions or billions of years to reach us, or never reach us due to cosmic expansion. There is no contradiction. The event is both sudden locally and vast cosmically. Now let us ask the most human question: should we be afraid? The rational answer is no, not in a practical daily sense. The probability, if the vacuum is metastable, appears extremely low on human and even stellar timescales. There are real dangers in the world that deserve attention: environmental damage, war, disease, asteroid detection, misuse of technology. Vacuum decay is not something we can monitor for tomorrow's forecast. It is not a reason to lose sleep,